بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. So in the previous lecture we have introduced neural network from the basics to deeper neural network, and now you understand the general concepts on how to calculate forward propagation and also backward propagation, and you understand now the shapes of the weight and the bias and the different outputs Z and A. Okay, but of course to train deep neural network this is like a complex operation, and it requires the tuning of several number of parameters, and these parameters, or what we call the hyperparameters, play important role on the performance of the model that will result from the training of the images in the dataset. So in this lecture we are going to see what are the techniques used for improving deep neural network, and basically we are going to talk about hyperparameter tuning, regularization and optimization. So we will start in this lecture by regularization, which is a technique on how to reduce the bias on and overfitting on the result. So from the previous lectures we have introduced the forward propagation and backward propagation in a deep neural network. We have considered a network of 5 layers. It has 4 hidden layers and 1 output layer, and we have calculated the forward propagation equations, the backward propagation equations, and also we have derived the shape of the W and B. We did the same also for the case of M training example, and of course A and Z will depend on the number of training example, which we call usually as batch. We usually have to set the batch size, which specifies how many images we are going to train in every epoch. So the learning outcome of this lecture is as follows. First, we will recall the different types of initialization, that lead to different results. You will recognize the importance of initialization in complex neural networks. You will recognize the difference between train, dev, and test dataset. We have talked about this before, and we're going to reintroduce this concept again because it is important when you train a neural network model. You will also learn how to diagnose the bias and the variance issues in your model, which is a common problem when you train a neural network. Maybe the results are biased, so we will understand what does it mean, a bias and a variance in training a neural network model. You will learn how to use regularization methods such as dropout and L2 regularization, and you will understand experimental issues in deep learning such as vanishing and exploding gradients, and learn how to deal with them. Okay, now let's talk about setting up the machine learning application. So usually when you have a machine learning model or deep neural network model, first of all you start by organizing your data, as you have learned in the Udemy course, and then you are going to build the first model. And of course the first model, it means that you are going to find some values for W and B that will transform this data into prediction, or transform the input data into an output. And then you are going to compare the output that you found with the output that you have to find. And if there is a big difference, I mean if the output that you find from the model is very much different from the output that you have to find, which is the ground truth, in this case you have to run some more updates, some more training. You have to update W and B again and again until your model becomes satisfactory. So this is the idea of a deep learning project. You have an idea, you do the code, you make an experiment, you get some results, and then you will see, okay, I am satisfied with the result, am I satisfied with the results? So if not, you have to do again. So when you do a new experiment, you have a lot of things that you can play with. You can play with the number of hidden layers. You can play with the number of hidden units in every layer. If you change any of these values, the whole network is going to change, and you will find completely different values of W and B. You will find completely different models. So you can also change the learning rate alpha, that will affect the performance of the trained model, the activation function, and many other things. You can even change the whole model. Okay, you can change the whole model and the architecture of the model. Any hyperparameter, if you change it, the resulting model will be completely different. So you want to have a systematic approach on how to change the different values or these hyperparameters in order to converge to the best model possible. Okay, but of course, don't always think that, okay, we can get the best possible from the first iteration. And don't try to have your objective, okay, I want to get the best thing from the first iteration. No, this doesn't work like this. So usually start even from a basic model, from a sample of data, and try to run, observe what are the different difficulties that you find, and you start tuning. Okay, sometimes you tune the learning parameters, sometimes you can tune the number of hidden layers. So you can play with these numbers until you can converge to a satisfactory model. So I'm going to show you in this lecture what are the different tips that you have to recognize and to take into consideration when you develop a machine learning and deep learning project. So of course, the first thing that we need to do is to divide our data set into train, dev, and test. I'm not going to spend too much time on this because we have already talked about this in the previous lectures, and also I have fully introduced this by demonstration into my course, my online course. So if you don't see it, please see it again. Okay, and I explain how to make the subdivision between train, validation, and test. But basically, the training data is the data that will be used for learning the parameters W and B. Okay, so this is what the model sees and used to learn the data. And the validation data set, it's used during the training, not to train the model, but to validate the model. And by validate, it means for every iteration, when the training identifies some values for W and B, we're going to use the validation data to check what is the resulting accuracy for the prediction on the validation data set. Okay, and this helps actually tune the model and guide the model on how many epoch we have to train it. So if we reach something good in the validation data set, we can stop the training. So the evaluation becomes more biased as skill on the validation data set is incorporated into the model configuration. So basically, we want that the validation data set contains images pretty much different from what we have in the training data set, so that the model is not biased by this data. What does it mean? So imagine that you train, for example, a classifier for cats. Okay, and let's imagine that you will use 100 images of cats that are, let's say, white color. Okay, all the images that you have are white color. So you're going to make the training, for example, 80 images of white color cat, and the validation as 20 images of white color cat. So maybe in this case you can have very good performance in the training and very good performance in the validation, because the difference between the validation dataset and the training dataset is very small. They are all cats and all of them are just white. Okay, so this is not, even if you get good training accuracy and good validation accuracy, it doesn't mean that your model is good enough to be general. This is why the preparation of the dataset is very, very, very important. And this is why I have a complete course on how to create your dataset. Okay, because if you don't create your dataset properly, at the end you will end up, okay, even if you get some good accuracy, this is completely meaningless. So, and one of the rules is that the training dataset and the validation dataset should have different distributions. So at the end, we try to understand if the model that you find through the training is general enough to also make correct and good predictions on the validation data set. And after we are satisfied of the validation data set, okay, if the model is not biased, in this case we can try on a completely different data set, that is the test data set, and provide an unbiased evaluation of the final model fit. So the test data set will contain images not in the validation and not in the training. And the idea is to have like, let's say, a third opinion. The first opinion will be from the trained data set, the second opinion will be from the validation data set, and the last opinion will be from the test data set, and finally the test data set if it is good enough. So it's very likely, we cannot say so we are certain 100% because we don't know about the other images that were not incorporated in the data set, but it's very likely that the model is good enough. Okay, and this is the life cycle. Yes.
So, Doctor,
Doctor, the test.
Validation.
Okay.
Sorry, Talan. The test after we finish training. Okay, so the test images, is it going, or can we make it to improve the model in any way or no?
No, we cannot say improve the model because the test data set is used at the end to use the model to predict the output from these test images. Okay, so it's just to see what is the test accuracy, basically, and some other metrics.
But Doctor, as you said, the test, we might have different images than the images we have in the data set, and it may be it not be good. It won't give us good accuracy. So in that case, we should take those images and retrain, or what?
Yeah, now if we imagine that we did our dataset properly in such that we have distributed in a proper way the images such that it is diverse in the training, validation, and test, and we have good diversity and everything. Now, if we are happy about the dataset itself, we're going to check the train accuracy, the validation accuracy, the test accuracy. If there is a major overfitting, it means if the accuracy of the training is much higher than the test accuracy, okay, it means that there is something wrong in the model. But if the training accuracy is very close to the test accuracy, so in this case we can say, okay, the model seems to be good enough. Okay, and we can take this model and put it to production. But of course, when you put it to production, you may end up seeing some low accuracy prediction. In this case, you can reiterate again by doing different techniques we are going to introduce later in order to have a better model. Okay?
Okay, thank you.
Yes, Talal.
So just as a reminder, the test dataset is only used during evaluation, right? So it's not used during the iterations of training.
No, it's not used, yes. It's after we finish the training and we take the model and we are 100% satisfied, we can actually make a prediction on the test dataset to check what is the validity of our model. Okay, so this is usually, we have to subdivide the dataset into 3 parts. Train, which is the largest number. Sometimes it may be 80%, sometimes it might be 95%, depending on the scale of the data that you have. And then another portion, this is for the validation, and the validation will not be used in the training, but will be used during the training to estimate the validation accuracy, but will not have any impact on the model. It will not have any impact on the values of W and B that the classifier will find during the training. Okay, but it's just another independent opinion for every set of W and B that is found during the training. And okay, finally, the test dataset will be used similar to the validation, but after completing the whole training. And the test dataset intends to provide an unbiased evaluation of a final model fit on the training dataset. Okay, now the question is how to divide train, validation, and test. So again, I explained this I demonstrated this in my course, so you can see it in detail for the implementation. But the rule that we use here, now, if we have, for example, small scale data, when we say small scale, for example, it's less than 10,000, 1,000 or 100, but you know, this is typical, but I cannot say this is a rule. You know, sometimes you can consider that 10,000 is good enough, especially if we have only 2 classes. But if we have 10,000 multiple classes and so on, we may have subdivision of 60%, 20%, 20%. It's also possible to make 80%, 10%, 10%. It's something in the range, okay? Because any data that you take for the validation and test, you will have less in the training. But if you consume all the data in the training, you will have a non-significant number of images that you will use for validation and testing. Okay, so basically you must make sure that the resulting number of images in validation and testing is sufficient. And this is why when we have a huge data set size, for example, I have 1 million images. So for 1 million images, what is 1% of 1 million? The 1% of 1 million is...
Going to 10,000.
Or 10,000.
Yeah, it's 10,000. It's still a huge number. So if I have 10,000 images into the validation and 10,000 images into the test, so I'm going to use this huge number to test my simulator. That's fine. That's great. But now imagine that you have 10,000 images in total and you make only 1%. What is the 1%?
It's going to be 100.
100, you know, 100 is not maybe very sufficient. Okay, 100 is not very sufficient. And for example, if you remember in our case when we had 40,000 images in the car dataset, I remember that we have used, I think 2% and 2%. It's around 1,700 images for the validation and 1,700 images for the test. Okay, and this corresponds to 2% and 2% and 96%. So how to make the subdivision depends on the scale of your data. Okay, just try to make sure that the number of images in the validation dataset and the test dataset is sufficient. Okay, is sufficient, and you will have, and also this also depends on the number of classes. Now, for example, if I have 10,000 images and I use 1%, so what does it mean? It means the validation will have 100 images and the test will have 100 images. But if I have only 2 classes, so I will have 50 images for validation and 50 images for the first class and 50 images for the second class. Okay, this is a good number. I can say that it's sufficient that I will evaluate 50 images in the first class and 50 images in the second class. But now imagine that you have, let's say, 20 classes. If you take 100 images and you divide by 20 classes, you will have how many? 5 classes, 5 images in every class. This is small. Okay, so I cannot say that this is a rule of thumb, but I usually would like to have more than 30 to 40 images, 50 images per class in the validation, and also the same in the test. Okay, but you know, it's everything depends on the scale of your data, and this is also another hyperparameter. You can tune it depending on many other things that you have, number of classes and the model that you are going to use, the accuracy that you want to achieve, and so many other things. Is it clear?
Yes.
Yes.
Yeah.
Okay. One of the other issues that we also face when you build a data set, and again, this is one of the things that I have explained in my lecture, is the mismatch between the train and test distributions. Okay? Now imagine that all your train data is high resolution cut like this. And imagine that your dev and test dataset, well, sometimes we can call it the validation dataset or the dev dataset. It means the same thing. It's low resolution. This may also create a problem because your model is trained on high resolution data and your test or maybe your final environment will be low resolution data, or maybe the opposite. So we try to make sure that the distribution of the trained dataset and the dev dataset are similar. And this is why in the course I show how to extract the distribution of the images in terms of number, in terms of the size, in terms of the resolution, because we need to make sure that we have like even distribution for the different type of images that we have into the dataset. But if you make, for example, different resolution in the train and in the dev, so the model that you train will be biased. يبدأ متأثر okay متأثر بالhigh resolution images. It will be influenced and biased by the high resolution images. So this is a very important point and that you have to make sure. Okay, some people don't care about these small tips and they will end up by building models that cannot generalize easily. But of course, now imagine that your final product, imagine that you are developing a deep learning model and at the end you are going only to use high resolution images. Okay, so in this case it's not a problem if you build your model from just high resolution images. But in any case, having a diversification will make the model more robust. Okay, the diversity of resolutions in the train, dev, and test dataset will make the model more robust. This is why when we do data collection, we try to collect anything. Okay, try to collect anything with different resolutions, with different accuracies, and with different width and height, to be able to have our model as much reliable as possible. Okay, now when you do a practical real-world deep learning project, you will face a situation similar to this one. So usually when you want to look for a data set, the first thing you will do, okay, let me find an existing data set on the internet. And maybe you go to Kaggle or you go to Google or to anything, and then you find a data set that contains, let's say, 100,000 images from the web. Okay, that's good. It's good to start with. And at the same time, you have collected images from your target distribution. Imagine that you do a model, for example, for a particular environment. You went to that environment and you took pictures, okay, from the same camera that you are going to use later on in the production when you deploy your model, and you collected 8,000 images from the target distribution. Now you have images collected from the web and images collected from the target distribution. Now the question, how are you going to do? Okay, how are you going to merge these two different types of images? The first approach, which some people find it intuitive, is to shuffle everything. I will take the 10,000 images from the web, the 8,000 images from the target distribution, and shuffle all them together. And then the resulting, I will just divide 100k images for the train, 200k images in the dev, and 200k images in the test. Okay, this seems reasonable, but this is not the best way. Okay, this is not the best way for this particular use case, because at the end, the model I would like to develop, I would like that it is for this distribution exactly. So I have more interest that my test dataset and dev dataset only makes part of the target distribution, because this is what I'm going to use for the distribution at the end. So another way that you can do, you can take 4,000 images from the target distribution and put them into, look now here, you will have at the end 100k images. Okay, it will be random from here, and so on. So you don't have any control about how many images will be from the target distribution here. But in this case, I can take half of it and I will divide it between the dev and the test data set. And the other 4K images, 4,000 images, I will shuffle them with the 100K images from the web. And this will constitute my training. So this is a better option, okay? Because at the end, when you train, you have already sufficient number from the target. You have also much more images to make your model more reliable. And the accuracy that you do for the dev and the test will reflect the accuracy that you would like to have later on when you deploy your model into a production environment. Okay, so this kind of distribution is much better than the previous distribution, although both of them are possible. واضح؟
Yes.
Okay, so let's see. Let me give you an example of mismatch distribution. Now imagine that you would like to develop a program that will identify people in Hajj and Umrah context, like this here. And we did this example. Several of you have already worked with us on this example. Okay, so maybe what you say, okay, I have to collect images, but the problem on the internet, I will not find enough images in the context of Hajj and Umrah, but I can find several other images in more general context. So maybe you go to a data set and you can find the image of persons from Europe or from US or from something else. And let's see that you train your model only on this. Is it 100% that is going to have to also correctly classify persons like in this image? Okay, so very likely not, because the context here is very different from the context here. And this is why it's always good to have, okay, now what I can say, let me take this data set, at least I will have much more instances to start from, and I will also collect more images from this context, from this distribution. And I will merge everything together in order to build my model. Okay?
Yes.
So the general rule here is that when you build the data set, you have to be careful on how to select your images in order for your model not to be biased, not to be influenced by certain type of distribution. And this is why, this is why we have to talk about bias and variance. Yes.
Since we have the output to be from specific context like Hajj, why we collect and train the model on different contexts? And does that, I think, that might affect the accuracy?
It's possible. I mean, if you can collect sufficient number of images from your target distribution, I mean, imagine that you can collect 1 million images from Hajj. Okay, now your model will be like this, will be much better for the Hajj context. But maybe it's gonna fail into another city. Okay? This is one thing. Another thing, maybe you don't have enough data from the Hajj context. So what you will do in this case? You will just use a small number of data. If you use small amount of data, your model is not going to be accurate, whatever you do. So you'll say, okay, I'm going to bring the images of persons from another context. At least, okay, they share some common features. So you will take benefit from the common features in other contexts, but of course, you will train the model by adding more images that have the features in the context of your target distribution. Okay, so now let's talk about the bias and the variance. Okay, so when you train a deep neural network, you can face different type of situations. Okay, so imagine that you train a neural network in order to make a regression, okay, for the blue points. Okay, a regression on the blue points. That means finding the line that goes through all these blue points. So if you have an output similar to this one, so this output is exactly, all the lines will come across exactly the points. So what will be the loss here? The loss will be completely zero. Yeah, zero. Okay, so we have a perfect match. But the problem, if you just any other point, is going to be outside. Okay, a point here or a point here or a point here and so on. So this problem here is called the overfitting. It means the model, it fits well the data set, but more than what it should. Okay, so it becomes not even a regression here, you just draw the lines point by point. Okay, so this kind of overfitting, usually you have, what does it mean in general? It means you have the highest accuracy possible for the train. Okay, look, this is the train, the points, the blue points are the train data. You have the highest accuracy possible, but if you have a test data, it will not be good enough. It will be much less. Okay, it will be much less. So the other problem that is completely the opposite is what we call underfitting. It means that the model fits to a very low extent the data set. Like for example, having here a very simple model, just line, making one regression line among everything. Okay, so in the case of overfitting, we have a very complex model. We can see it as a polynomial regression with high degree here. And here you have a polynomial regression, but it's with degree 1, just a line. Okay, a simple line. Okay, so here we have an underfitting because the model is too simple. Here the model is too complex, and here the model is too simple to feed the data. Okay, so these are the two extreme cases. In the case of overfitting, we say that we have a high variance. Okay, high variance because the model is very complex. And here, in the case of underfitting, we say that we have a high bias. Okay, so this is the definition of variance and bias. The bias is in the case when you have an underfitting, the model is too simple, and the overfitting will lead to having high variance. And making a good balance, we could have something similar to this one. Look, you have the same data points, and this curve, okay, it will have a little bit maybe less accuracy than this model, but it is more general as a regression as compared to this one and this one. So in this case here we have low bias and low variance, and this is the models that we try to find when we train a neural network model. Of course, here we have a very simple case with input X and output Y, so we have just two-dimensional, but the neural network is multi-dimensional. I mean, we can have the same thing. We can think about that the curves will be multi-dimensional. And you can read more about this into this towarddatascience.com, and I really recommend. There are plenty of nice articles that you can find on the websites of Medium and Towards Data Science. They provide very nice and simple explanation of several concepts related to artificial intelligence, neural network, and so on.
Doctor?
Yes.
So we understood that overfitting and underfitting could be caused by bad models. But what about the data set? How does it influence overfitting and underfitting? I mean, I know in overfitting, we can have data that is not diverse enough, or maybe that is not big enough. But how does the data influence underfitting?
No, we cannot say that the data may have an influence if you don't provide an appropriate distribution of the data. And this is something that I have explained into the practical lecture. Okay, but basically the data is going to be used to build a model. Okay, both in the case of overfitting and underfitting, we have models, but this model is perfect with the trained data, but it's very complex. Okay, in the sense that if you have some other points, okay, it always, maybe it's going to be always fail outside. Okay, here you have a simple model. Okay, a simple model, but you can see that the gap is very high between the model and the point itself. So what is desired is to have something in between. We don't want to have a perfect model for the trained data and bad model for the test and the validation. This is something that we want to avoid. What does it mean like this? It means that our model fails to generalize. We cannot generalize it because now the training data, this is the data that is used to build the model, but later on you're going to take the model and deploy it with data that you have never seen before. And this is why we, as we introduced before, we use the def data and the test data, which is data not seen during the training that will just be used to evaluate. Okay, so although this model is perfect for matching the training data, okay, it will not be good enough for matching other data not in this model. You see what I mean? Whatever data that you are going to add here or here, you will always have a gap between the zero loss that you find in the training and the greater than zero loss that you will find when you have a different type of data. Okay, so what we want to have a model such that the accuracy of the training and the accuracy of the validation is similar. Okay, it's never going to be exactly the same, but we want the gap to be, for example, 1% or maximum 2%. But if you have a gap of 10%, it means that you have something wrong in your model, and your model is not general enough. واضح?
Yes. So overfitting happens when we do too much training on data that is not comprehensive enough. So we're going to have a complex model that is trained on a very small set of data that does not cover all the cases.
No, your data can be comprehensive, but it means that your model just have a perfect match with your training data, but doesn't have the same matching of other data not seen in. So the problem is from the model itself, not necessarily from the data.
That's the symptom of the problem.
Yes.
Right?
Yes. And this is why now, if we look at the definitions of the bias and the variance, so the bias is the difference between the average prediction, in this case it's this line, of our model and the correct value. This is the definition. So here we have high bias because the average prediction is very high between the points, the distance between the points and the line. So, and this model with high bias pays very little attention to the training data. Okay, this is what does it mean. It's too simplistic. It oversimplifies the model. Okay, this line, it's a regression line, but it's oversimplifying the model. It always leads to high error on the training and test data. So if it fails on the test, if it fails on the trained data, it's more likely to fail on the data of the testing and the validation because, okay, this model was used from this data and it has a high bias. So it should be even higher when you have a test and validation data. On the other side, for the overfitting, so it has high variance. So what is the definition of variance? Is the variability of the model prediction for a given data point or a value which tells us the spread of our data. Look at the prediction. Sometimes we go up and then we go down and then we go up and then up and then down. So there is a lot of changes in the prediction. And now there is no change. It's kind of constant line. Here there is a lot of variance in the prediction. Okay, the prediction here is different from the prediction here, is different from the prediction here. However, here it's smoother. Okay, the transition between prediction is smooth. It goes smoothly. However, here it has high variance. So the model with high variance pays a lot of data to the training data. Okay, so the resulting model here is very much tied and very much related to the trained data. However, it fails to generalize. on the data which it hasn't seen before. And this is the problem of overfitting. And usually this means that your train accuracy is much higher than your test and validation accuracy. And this is like the common problem that most of the data scientists who work on deep learning and machine learning face, which is very common problem. And we will see later on some of the techniques that we call regularization that will attempt to reduce the problem of overfitting. So as a result, such model performs very well on the trained data, but has high error rate on the test data. This is the definition of the bias and also the definition of the variance. Any question here?
Yes. Which is more common, overfitting or underfitting? Usually.
Overfitting is more common because usually we build complex models. Okay, so sometimes this model, and we have seen this in the example of cat not cat. If you remember in TensorFlow, the very simple example, we have almost 100% of accuracy in the train, but we have very small percentage, like 60% only, for the test data set. And this is the problem of overfitting, because the model was trained to be perfect with the trained data, but it is not good enough for the test data. So we see that we have overfitting problem here.
Yes. So what could cause underfitting? Sorry, I'm asking too much. But,
yes. No, it's a very good question, by the way. So underfitting, basically, if you use a small neural network, for large amount of data. So in this case, you have only a small amount of neurons that are going to, so the model oversimplifies the data. And the problem of overfitting is when you have a large model, but your data maybe is not sufficient or is not sufficient to train all the different nodes in your layers. Okay, so underfitting, basically it results from having an architecture that is shallow, that is very simple. It's like you are estimating a complex neural network with just a regression line, which is the simplest model. If you remember the first regression line that we have done in the first lecture. Yeah. So this model, it has W and B, but it's oversimplified. So in this case, you will have underfitting. And overfitting, it's the opposite. Basically, you have, let's say, a rich or a deep architecture of a neural network. So it will be pretty much perfect for the trained data, but will not be able to generalize sufficiently for the validation and the test data. واضح؟
Dr. and assignment.
Yes.
Cat assignment, when we use logistic regression and we get really low accuracy, it was because underfitting or overfitting?
When we got low training test, we got test accuracy, low test accuracy, right? Or training.
It was because test accuracy, doctor.
Yeah, the test accuracy, usually this means that the overfitting. So overfitting, basically it means that your test accuracy is much lower than your train accuracy.
Okay.
Okay, this is just another slide that explains a little bit more the detail. But here, for example, on finding the boundary between the blue dots and the red dots. So imagine that you have a model that finds the green boundary. What do you think about this model? It's perfect.
Overfitting.
Good in training, but not good in testing.
It's good in training, but it's overfitting. Look at this dot here. Where it is located? It's located inside the blue. صح ولا؟ So this is kind of an outlier.
Yes.
But the model, because it is very much influenced by the training, it considers this as blue. So it takes this territory for the red. Okay. However, we can see this here visually, and maybe this one is visually, and this one is visually. All of them are inside the blue border, and This one is inside the red border, but because of overfitting, okay, it makes a perfect match of all the points individually, but it fails to generalize. Okay, now if we look at the other extreme, which is underfitting, let's make the subdivision just using this line. But look now, look at this point. Okay, they are considered as blue. However, they are more toward the red colors. Same thing here. Okay, so something in the middle. Okay, it's this black curve. And of course, maybe, okay, these outliers, it doesn't matter if they are not counted within the correct region, but because they are located actually in, they are considered kind of outlier. So even if we classify them differently, it's not a big deal because they are considered as outlier. So the best model is the one that is able to filter the noise. So we can consider these points or these points here can be considered as the noise, and the model shouldn't care about that noise. Okay, so it happened when they train a model a lot over the noisy data. Okay, we can see it in different manner. That the model, in case of overfitting, it also includes the noisy data or the outliers, which is not a required behavior. Okay, however, a good model is going to discard these outliers and put them, okay, outside of the equation, so that it only cares about the most likely, okay, the most likely data. واضح المثال؟
واضح دكتور.
واضح.
Okay, let's have a few examples now. For example, when you train a model, okay, how to analyze the data that you get after the training. So basically, after you do the training, you will find a train error, a test error. Okay, so imagine that your train error is 1% and your test error is 11%. What is the result here?
Overfitting.
Yes, we have high variance, and it means we have overfitting because the model fails to generalize. It's very good in the training, but it's very bad. Okay, it's the error or the accuracy of the test or the error of the test is much higher. The test error is much higher than the train error. Now imagine that you have a train error 15% and the test error 16%.
It's bad for both.
Underfitting.
No, here we have both. We have high variance and we have high bias. Okay, we don't have high variance. We have high bias. Okay, this is underfitting. The model is bad for train and for test. It is too simple. The model is too simple to represent the data. This is why we get a bad train error and a bad test error. And this is what we have here, the high bias or underfitting. Now imagine that the train error is 15% and the test error is 30%.
Underfitting.
This will be both.
We have both. We have high bias, okay, because the difference, we have high bias because both the train error and test error are very high, and we have high variance because the test error is also much higher than the train error, and both of them are high. So in this case, we have overfitting and underfitting. And finally, if we have 0.5% and 1%, so this means we have low bias and low variance, and this is the good fitting that we want to achieve. Okay, so this is very important for you to understand, to be able to appropriately analyze the outcome of deep learning or neural network project. Okay, when you look at the train error and the test error, you will be able to identify what is the issue. Do you have high variance? Do you have high bias? So if you have high variance, it means you have overfitting. And now the question, okay, how we can overcome the overfitting? We're going to provide response to that in the next couple of slides. But the most important thing, after you finish the result, after you do the evaluation, you must be able to interpret correctly the type of the fitting, whether you have a good fitting or underfitting or overfitting.
Doctor,
Yes.
to have a good fitting, what's the percentage that we should aim for train error and test error?
Yeah.
Only this fixed value 0.5 and 1%.
Well, it's usually difficult to tell because it depends on the complexity and also on the architecture of your model. You know, in some cases you want to achieve 1% or something even lower than 1%. And sometimes if you are at 5%, that's fine. Okay, sometimes the data is very complex such that you know in advance you're not able to find like 100% accuracy. And in general, in deep learning, it's very hard to find 100% accuracy. If not, it's almost impossible. And sometimes if you find 100% accuracy, it means you have something wrong, maybe in your model, or if you have your data is not correct and so on. But usually, you know, 5% error or 6% error, you know, this is something that might be acceptable. In some more complex situations, you may even go at 10%, for example, with segmentation or more complex neural network problems, we can go even lower in terms of accuracy. But for simple classification problems, I mean, something above 5% should be fine, but it depends on what is your required accuracy and what are you going to use the model for. If you are going to use the model for something that you need high accuracy, so in this case, you need to work more in order to reduce it further. Okay.
Okay.
Any other question? Well, okay, so this plot shows the bias and the variance trade-off. And to build a good model, we need to find a good balance between the bias and variance, such that it minimizes the total error. So what is the error here? The total error of a model. Imagine that you train a model. Okay, so here we have the model complexity, and here we have the model error. Of course, if you increase the model complexity, you can have smaller bias and higher variance. So the model complexity, what does it mean, the model complexity?
Type of image vector, or how many features?
Yes, how many features to extract? Yes, the number of
How many
nodes.
new?
We can say the number of nodes and the number of layers. Okay, they will identify a complex model. It will have more nodes and more layers, something like deeper and wider. You will increase the model complexity. So if you increase the model complexity, you may run more likely into overfitting, high variance. Okay, and the bias will be lower because the model will not oversimplify the problem. If you reduce the complexity of the model, so you go in the either direction, the bias is going to increase and the variance is going to decrease. You will have more risk of underfitting and lower risk of overfitting. Okay, so this zone here, we can say that this is the zone of underfitting, and the zone here is the zone of overfitting. And you try to find a model complexity, okay, such that it will give you the lowest error possible. Okay, you try to find the model complexity, the lowest. Maybe you can find here a model at this point. Okay, but the problem is you will have higher variance. Okay, so the objective here is to find the model that can give me the lowest error possible. Okay, and the error here that we will find okay, will depend on the bias, will depend on the variance, and on an additional error. So how do we calculate the bias? So basically it is the expected number of the output minus the ground truth. Okay, minus the ground truth, it will give me the bias. Okay, it's like the distance between the model and the ground truth value. The distance between the model, this is the model, and this is the ground truth value, the distance, and we make the square. It is going to give me the bias, the square of the bias. So the variance here is the estimated value minus the model square, and we take the average. Okay, the average of all of them. So we try to reduce the good model that provides the best fit is the model that will reduce this error, the resulting error from the bias and the resulting error from the variance plus certain sigma, which is an irreducible error. So in any case, you will always have an error in your model.
Doctor?
Yes.
When we calculate the bias and variance, how we know this number is high or this number is low? What will decide?
No, yes, we decide basically from a table similar to this one. Okay, so when you analyze when you analyze the train and test error, you will be able to know whether you have a high variance or a high bias. This is just an equation. Okay, you can use it to calculate the error, but basically when you develop the training, you will rely on the difference between the train error and the test error. Okay. Yes.
Doctor, this question, can you go back to the slide we're in?
Yeah.
Okay. So you said that we can have the line exactly in the intersection, but this will result in high variance. But we chose to have higher bias and lower variance. Why is that?
Can you repeat, Talal?
You said that we can have the line exactly in the intersection, but this will result in higher variance, which is supposedly a bad thing. But why did we choose to have slightly higher bias and slightly lower variance?
No, this is not, we didn't choose. Now, when you do the training, you're not sure that you will be here or here. Okay, you can be in any region here. So basically, you want to find the model that will provide the lowest value. This is like your real experiments. Okay, you conduct some experiments, it gives you this error or these errors here. Okay, so we'll try to find the one that will provide the best trade-off between the both.
Okay.
Yeah.
Doctor?
Let's say this is just here illustrative about the relation between the bias, the model complexity, and the error, and this one about the variance. But here, for example, this is let's say the result of several training. Okay, you did a training with high model complexity and another high model complexity and someone a bit lower and then low model complexity. So after many experiments, you find that this model is going to give you the lowest error. Okay, so you choose it. You see what I mean?
So just based on testing.
Yes. Maybe, okay, when you go to this model, when you go to this model complexity here, it will give you smaller bias, but a bit higher variance. Okay, so you try to minimize both. This is the idea. You try to minimize both. And you have then, yes.
It is just like a summation of both of them, صح?
Yes.
So it's good.
Yes, you minimize the sum of both, the bias and the variance.
Doctor?
Yes.
In the training, the value of W and B will be updated automatically, right? يعني in each iteration.
The value of
W
Yes,
and B
of
will be
course.
updated
Yeah,
Yes.
it will be updated in the backward propagation.
Yes. But what about the number of layers and nodes? It will be updated automatically, or
No,
we have to do it
no.
manually?
No, this is your architecture. You fix the architecture in advance. All hyperparameters are fixed. Okay, all hyperparameters are fixed when you start an experiment. Of course, with some exceptions. I mean, the learning rate, you can change it over time. But in general, you don't change the number of nodes in the layer and the number of layers. But of course, I'm going to show you a technique that will change the number of nodes in some of the ways. But I will show it later.
يعني دكتور, when we start the training, the only values that will be changed, W and B and the learning rate
Yes.
in the model.
The learning rate doesn't change. Only هو المفروض it's not learnable, the learning rate. Usually it is fixed. Like sometimes what we do in real experiments, we are going to start from a learning rate, and when we train for several epochs, we are going to reduce the learning rate باش يولي التقدم نحو الoptimal solution أبطأ, slower.
Yes. To achieve the minimum error,
Yeah.
right?
Yes. So the idea is that we start with high learning rate and then it will decrease with the number of epochs. لكن it doesn't mean that it's going to change because it is a learnable parameter. It is not learnable. What is learnable is only W and B. These are the two parameters that will be learned during the training. واضح؟
Yes, clear.
Doctor,
Yes.
what does A means in the equation?
Which A?
The E.
Expected value, the average.
Okay.
Yeah. Okay, let's look on how to analyze the variance and the bias. So imagine that you made some training and you find high variance. Okay, high variance, it means you have overfitting. Okay, the cause of the poor performance is high variance. So what are the symptoms? How do you know this? When we say symptoms, is what are the things you observe to understand that there is a high bias. First, the training error is much lower than the test error. This is basically the most important symptom. Or the train error is lower than epsilon. Or the test error is above epsilon. Okay, so maybe we can have a certain threshold. Okay, the train error is smaller than threshold and the test error is above the threshold. And basically it means that the train error is lower than the test error. We have a big gap. So how to overcome this? Maybe this model doesn't have enough data. So we need to do data augmentation. And data augmentation, we can do it by collecting more data and add it to our data set. Or also there are some techniques in TensorFlow for making data augmentation, which we are going to introduce maybe in some next lectures. Okay, so the first thing that we will think about when we have overfitting is maybe we need to add more training data to train our model. Like, and sometimes the data might not be available or might not be easily available. So in this case, we may try to reduce our model complexity because models are prone to complex models are prone to high variance. So what does it mean? Imagine that you made a first training. For example, you have used a model with 200 layers and you find that you have overfitting. So maybe what you can do, we can use another model with only 100 layers or with 50 layers only. So we try to reduce the complexity of the models to have smaller number of layers, smaller number of nodes. These are the two possible techniques, and of course we will see some other techniques that are called regularization that will allow also to reduce the overfitting. Now in
Doctor?
case, yes,
When we change the brightness of the image and rotate the image, are these an examples of
this is an
augmentation?
example of data augmentation. Yes, you can make transformation of the same image. It's one of the possible ways to make the robot a little bit more robust, but it's not the same as you add completely new images to your model. But it's better than not doing that.
Yeah.
Okay, yeah. So in the case of high bias, the model being used is not robust enough because it oversimplifies the data and is not accurate for the prediction. And the symptom here is clear, is when your train error is very high. If your train error is higher than certain threshold, in this case, you know that you have high bias and you have underfitting. And one of the techniques that you can do is to use more complex model. Maybe your model is like very simple. Okay, it doesn't have enough nodes to extract all the important features that you have provided from the data. Okay, and also you can add more features. I mean by adding more hidden nodes or more hidden layers. Okay, so this is the workflow. If you have high bias, okay, try a bigger network, try to train for a longer time, and try different neural network architecture. If you don't have high bias, you will check the variance. If you have a high variance, then you need maybe more data, or you need to apply regularization techniques, or you try different neural network architectures. And if you don't have neither a high bias or a high model, you are very lucky, and it seems that your model is done and is fine to test it in a real application. Okay, now we will talk about the regularization techniques, but maybe I can stop at this time and put this for the next week, and maybe we can talk a little bit about